Hello and welcome. Today I'm going to explain what is light in simple terms. Let's start off with an analogy. We have a buoy in water. This is a buoy. This is water. Imagine that buoy has a handle on it where you can shake the buoy up and down. Now if you shake that buoy up and down really high, you're going to make waves that are really high. If you shake that buoy up and down really fast, you're going to make waves that are very closely spaced together. If you don't shake the buoy up and down really high or very fast, well, in this case, you're not shaking it very high. Now, if you don't shake it very high or very fast, your waves are going to be pretty spread out. So now, if we take an electron, which I'll denote by E minus, and we shake that electron up and down, the electron's going to make a wave. It's going to go in both directions too. So now, if we think about the analogy we just drew, let's label this 1, 2, 3. Okay, so we need to understand some terms here. Number 1 has a high amplitude. So the height of the wave is the amplitude. Number 2, the waves have a very high frequency, we would say, and a short wavelength. Number 3 has a very long wavelength and a small frequency. The wavelength is the distance from trough to trough, or peak to peak, or center of the wave to center of the wave. As long as you go through one complete cycle and return to where you started, that's one wavelength. So here to here, we can say. And we call that lambda, which is the Greek letter for L. So that's wavelength. So now, compare 2 and 3. Notice when you have a high frequency, you have a small wavelength, and vice versa. That's because the speed of a wave, the velocity v, is the wavelength times the frequency nu. So nu is the frequency, v is the velocity of the wave. The wavelength has units of distance, or meters. Nu has units of 1 over seconds, or you might see it hertz. It's the same thing. It's the number of cycles per second is the frequency. The velocity is in meters per second, like any velocity. If you were driving a car down a road, you drive a certain number of meters each second. So, now just like we had the buoy making waves in water, well, the electron makes waves in the electromagnetic field. And waves in the electromagnetic field are a little bit different than waves in water, in that waves in the electromagnetic field always move at a speed, call it c, which is just the velocity of light, and it's equal to 300,000 kilometers per second. Nothing can go faster than that. And the thing about light is it always moves at that speed. So if you think about, you're on a boat, right? I'm not a very great drawer, but okay. We're on a boat. That's our boat. And you're stationary in water. Imagine some guy is making waves by a buoy here. And imagine those waves have a velocity of, I don't know, 10 meters a second, let's say. Well, you're going to see the wave traveling 10 meters a second. Now, if there's another guy on a boat, and he's traveling forward at 5 meters a second, and those same waves are being made, well, he's going to see the water waves moving at 5 meters a second. Light is different in that both of these people, if they were looking at light, would see the light moving at 300,000 kilometers per second. Now, you might not think that makes sense, but it does make sense if the perception of time for both of these people is different. And that's as far as I'm going to get into that. If you want to learn more, look up videos on relativity. Now you can notice we can create waves with a short wavelength or a long wavelength or anywhere in between. So that region that we can create ones with long wavelengths, short wavelengths, is a spectrum. And the different wavelengths that light can have is the electromagnetic, I'll call it EM, spectrum. So you can have long wavelength. Pencil keeps breaking. Long wavelengths. And you can get short ones, and shorter, and shorter, and shorter. And, you know, they're really close right there. So the longest light wavelengths, so notice the wavelengths over here are long, the wavelengths over here are short. So let's call lambda, it's wavelength, nu is the frequency. So we have long wavelengths over here, we got small frequencies over here. In this region, let me draw this one more line down. So we're going to name each region. This region is called the radio frequencies. The next region, the next shortest wavelengths, is the microwave region. And then you got infrared, IR, and then you got visible, and then you got ultraviolet, and then you got X-rays. And gamma rays are the shortest wavelengths. Radio waves have a wavelength of, this is very, very rough, let's say like 100 meters, something like that. Anywhere between like 1 and 100 meters. Microwaves have wavelengths of about 1 millimeter, or 10 to the minus 3 meters. Infrared wavelengths are about a millionth of a meter, 10 to the minus 6. Visible is on like hundreds of nanometers, so it'd be 10 to the minus 7 meters. UV is about 10 to the minus 8. X-ray is on the order of angstroms, or 10 to the minus 10 meters. Gamma is very small, let's just say 10 to the negative 15 meters. Now if we use the equation, C, the speed of light, equals the light's wavelength times the light's frequency, and we plug these numbers up and solve for C, we get nu equals C over lambda. So radio waves have a frequency of 300,000 kilometers per second. Well, let's write 2 more zeros and just write meters. Meters per second divided by 100 meters. Punch that in your calculator, you're going to get 3 times 10 to the 6 hertz, or 1 over seconds. Do that for microwave, you get 3 times 10 to the 11th hertz. Do that for infrared, you get 3 times 10 to the 14th. So on and so forth. These all have a 3 in front of them, but I won't write that anymore. 10 to the 18 for X-rays, 10 to the 23 for gamma rays. Now, just to get a sense of how fast these frequencies are, let's try to think of some everyday frequencies. So, say you're walking on the sidewalk, right? Walking down the sidewalk, moving, I don't know how fast you're moving, but you probably take an average of 1 or 2 steps per second. So about, 1 to 2 hertz is your frequency of your feet hitting the ground. And if you're running, you probably have a frequency of maybe twice that, 4 hertz. So each second, your feet are hitting the ground 4 times, maybe. Now, if we think of things a little faster, maybe you can imagine raindrops hitting the ground. So take the roof of your house, right? And imagine it's raining. Each second, let's say 1,000,000 raindrops hit your roof. So that means the frequency of raindrops on your roof is about 10 to the 6 hertz. That's radio waves. That's the frequency of radio waves. Things that happen faster, let's see. I can't really think of a good idea. Well, the electricity in your household outlets, at least if you live in America, electricity, AC, goes at 120 hertz. So that means it cycles not on and off, but it switches directions in a way 120 times every second. So that's giving you an idea of everyday frequencies. And light is so much faster than, well, most of these frequencies, besides the raindrop hitting the roof. It's very hard to think of an analogy for visible light, for instance. So visible light has a frequency of 10 to the 15th hertz. And 10 to the 15 is 1 with 15 zeros at it, after it. And let's see. I believe a billion is 10 to the 12th. So 10 to the 15th is a quadrillion. So if you imagine light passing you, you're sitting here, and a light wave is passing you. At each second, 1 quadrillion cycles of light are passing through you. Now that's pretty fast. Let's zoom into the visible region here. Okay? So you have long wavelengths of the visible region and shorter ones. So visible light, red has the longest wavelengths, blue has the shortest. And if you do your Roy G. Biv, you can guess the ones in between. So you got red, orange, yellow, green, blue, and violets over here. Now red has a wavelength of approximately 800 to 700 nanometers. Orange is about 650 nanometers. Yellow is about 600. Green is 550-ish. Blue is about 500 to pretty much 400. Violet is the very small 400s. So maybe like 410 nanometers. So that's a very brief, simple overview of what is light. Another thing that I didn't even mention the whole video is that another name for light, if you want to sound fancy, is electromagnetic radiation. And I'll be talking about why it's called that in the next video. Thank you for watching and have a good day.